Welcome to STEM School. The third proof is proof by exhaustion. Now let's get cracking. Proof by exhaustion. Now the first thing is to define what proof by exhaustion is. So I'm going to start this one by saying in proof by exhaustion, you need to break things down into two or more cases. So in doing so, you need to make sure that the cases cover all possible situations. So cases should cover all possible situations. That you will understand when we do an example. So cases should cover all possible situations. Then prove separately. So that's one thing we have to do here. So then we prove separately each cases. So then we prove separately each cases. Or each case. So separately we prove each case. Now, the best way to do this is to give an example. So let's go for an example, because that way it's clear on what we need to do. So I'm going to write an example. So the first example is, that's an example. It says prove. We're going to prove the following statements. And what is the statements? What are the statements? Sorry. So for any integer x, comma, for any integer x, the value of fx, which is equal to x cubed plus x plus 1, is an odd integer. Okay, so that is the statement that we're looking at, or statements. For any integer x, the value of fx is an odd integer. Now what we need to do is to now break this statement down and then try and justify each case. So we need to try and prove each case separately. So how can we break this statement down? Well, the keyword here is that any integer x. I think perhaps it might be better for me to remind everyone that the definition for an integer is you would have a positive whole number you would have a 0, that's an integer, and you would also have a negative, I should write that in capital, whole number. So perhaps if I put plus 2, 0 obviously is 0, 0 is an even number, and minus 2, that will be an integer. So a positive whole number in 0 and a negative whole number. Now because the two cases we want to look at is, the first case should be an even number. So what I need to do is to write down these two cases. So case 1, as case 1, let's if x is an even number. So if x is an even number, that's case 1. And case 2 would be if x is odd number. So let me use the capital there, number. And let me separate these two cases because I'm going to prove them. There you go, these are the two cases. Case 1, x is an even number and x is odd number. As an integer, you could have a positive even number or positive odd number. You can have a negative even number or negative odd number. So what is the definition of an even number? We all know what definition of an even number is. So let's say x equals 2n, where n is an integer in this case, where n is an integer. Right. So that's the first and in the case of odd number, x would be 2n plus 1. So I need to solve the first case in this case because this is any integer, and because we're referring to the fact that the function fx will have an odd integer for any integer of x. So that means we have to look at even integer of x and odd integer of x. And in this case, so we just have to replace the fx, which is x cubed plus x plus 1. We have to replace that with 2n. f2n, that will become 2n cubed plus 2n plus 1, which means 2 to the power of 3 n cubed plus 2n plus 1. 2 to the power of 3 is 2 times 2, 4, 4 times 2, 8. So that's 8 n cubed plus 2n plus 1. Now, 8n cubed and plus 2n, the two of them have they have 2 in common. There's 2 here and there's 2 in there. So if I take 2 out, so I'm going to get 4n cubed plus n, close bracket, plus 1. And in this case, still I'm doing f2n. So in this case, may I say that let 4n cubed plus n equals p, and therefore I would have equals p, and therefore I would have 2p plus 1. 2p plus 1. And what would that give me? That would be an odd number. So that's an odd number. 2p plus 1 is odd number. So yes, in that case, for any even number of x, the fx will be an odd number. So that's true. And that's how you prove that. That's how you justify that. So 2p plus 1 is odd number. Right. What about when x is odd number, number integer? Well, so an odd number is 2n plus 1. So fx is x cubed plus x plus 1, and f2n, so I'm replacing x with 2n plus 1, 2n plus 1. So that's plus 1, by the way. So I'm going to get 2n plus 1 cube plus 2n plus 1 for the x plus 1. Now I need to do expansion here, which is the expansion of a cube. So to do an expansion of a cube, I am going to do that up here because I need the space to finish up my work. So I'm going to do that here. So if I have a plus b, I hope you can see that, a plus b to power cube. So I'm going to use binomial first of all. Well, actually that means that that's a plus b times a plus b times a plus b. But using binomial expansion, so I'm just going to do a cube plus a cube b0 plus a squared b1 plus a b squared a1b squared plus b cube a0. But anything to power 0 is 1, obviously. So a to power of 0 is 1, b to power of 0 is 1. So that would be a cube plus a squared b plus ab squared plus b cube. Now I need to also write the coefficients of this expansion using a Pascal triangle for the coefficient. Pascal triangle is basically if you have a plus b to power of 0, that will be just 1. Anything to power 0 is 1. If you have a plus b to power of 1, the coefficient of these two will just be 1, 1. That's 1a plus 1b. And if you have a plus b to the power of 2, then the coefficient will be, you start with 1, 1 plus 1 is 2, and then you finish with 1. And if you have a plus b to the power of 3, again you start with 1, 1 plus 2 is 3, 2 plus 1 is 3, and then you finish with 1. So these are the coefficients of a plus b to the power of 3. So I may come back here and put those in. So I would then have a cube plus 3a squared b plus 3ab squared plus b cube. So that's my expansion there. Now I can use that to finish up here what I need to do for that expansion here, where my a in this expansion, my a equals 2n and my b equals 1. So that's my expansion there. So what I need to do now is put those in back here. I'm going to write 2n, that's a cube, plus 3 2n to the power of 2, and then b, which is 1 to the power of 1, so that's just 1, plus 3 into bracket 2n to the power of 1, and b squared, which is 1 squared, so that's just 1, plus b cube, which is 1 cube, so that's just 1, and then I need, that's just, that expansion is for those here now, and then I need to put plus 2n plus 1, then plus 1. So remember, I'm just putting a there and replacing that, and then 1 is b, so that goes in there. So now what I need to do is continue to do my expansion, so I get 2 to the power of 3, which is 8n cube, plus now 2 to the power of 2 to the power of 2 times 3, that would be 12. 2 to the power of 2 is 4, 4 times 3 is 12, 12n squared, plus 3 times 2 is 6n, plus 1, plus 2n, plus 1, plus 1. So I will get 8n cube plus 12n squared plus 8n, 2n plus 6n, 6n plus 2n is 8n, plus, right, 1 plus 1 plus 1 is 3, but I'm going to write 2 plus 1. And there's a reason for that, because I'm going to take a common factor from here to there. A common factor is 2, so I'm going to get 4. Well, I'll take a 2 out, so I get 4n cube plus 6n squared plus 4n plus 1, and then I get plus 1 at the end here. So if I let, what I'm going to do now is I'm going to let k equals 4n cube plus 6n squared plus 4n plus 1. So that's what I'm going to do. I'm going to let k equals those. So that means all these here is k. So what I'm getting now is I'm going to get, closing to the end of the calculation now, so I'm going to get 2k plus 1. So that's odd number, so that's odd. So I have calculated x as an even number. I got odd value, 2p plus 1. I also calculated x as odd number. I also get 2k plus 1. Therefore, the statement is, so now proving the statement now, that this statement is true, that for any integer value of x, for any integer values of x, the value of fx equals x cubed plus x plus 1 is an odd integer. The statement is true.